In this video, I'm going to discuss fractional exponents, exponents that are fractions. So if I had like 4 to the 1/2 power or 27 to the 1/3 power, what in the world do those powers simplify to, if they could even be simplified? All right, so as I said in a previous video, the way that we interpret these is these are man-made, so people simply define these the way that made the most sense. All right, let me show you something that makes sense. What would be a good way to think about fractional exponents? First of all, remember the product rule. If I have a power x to the a, x to the b, that equals x to the a plus b. So let's use that rule to see if we can understand a fractional exponent. See if we could come to a good definition. All right. So I don't know what x to the 1/2. Well, I do, but let's pretend we didn't. Okay. So x to the 1/2 times x to the 1/2. Now, according to our power rule that I just wrote, that should be the same as x to the 1/2 plus 1/2, or x to the 1. Okay? Furthermore, anything multiplied by itself is equal to itself squared. So apparently x to the 1/2 squared is equal to x. Okay? So you may recall that to get rid of an exponent of 2 from both sides of or if it's on one side of an equation, if it's on both, even better, but what you do to get rid of it is you take the square root of both sides. And if we do that, we arrive at the expression that x to the 1/2 is equal to the square root of x. Now I realize in general we would have to assume that x to the 1/2 could also be minus root x, right? If you have something if something squared equals a number, then that something could be plus or minus the square root. All right. So, but to keep things simple, we're going to assume that all the variable values are positive. Okay. In fact, that's how we're going to define x to the 1/2. We're going to define it as the positive square root of x. Okay. So and why did we define it that way? Because that's what meshed with this original product power rule. All right. Put that in the back of your mind. Let's do something similar now for x to the 1/3. Let's take x to the 1/3 and multiply 3 of those guys together. That's equal to x to the 1/3 plus 1/3 plus 1/3. Now we haven't defined the rules for fractional exponents, but if they work the same, then this would be x to the 1. All right, or x. Okay, so in other words, x to the 1/3 cubed is equal to x, but only if this rule even holds for fractional powers. Okay, which we would like it to hold. All right, so the only way to get rid of the 3 exponent is to take the cube root of both sides. So look at what we have there. So the 1/2 exponent meshed well with the square root of x. 1/3 meshes well with the cube root of x. Okay, you can keep doing this treatment for different fractions, 1 over some other natural number, and you will keep getting this pattern. So let me summarize if you haven't caught on yet. So x to the 1 divided by k, apparently a good definition would be it's the kth root of x. So k denotes the type of root. Okay, now that's all well and good, but you might ask, well, but what about if the fraction doesn't have a 1 in the top, in the numerator? Not all fractions are 1 over k form. All right, well, so let's say that it was 3 over k. Okay, so how should we interpret something like 3 over k? Well, that's the same as 1 over k times 1 over k times 1 over k. So that's apparently the same as the kth root of x times the kth root of x times the kth root of x, which is equal to a single kth root of x cubed. Okay? And whether it was, if the 3 was a 5, then you'd have 5 kth roots of x, and so the inside of the, or under the root, you'd have x to the 5. Okay? So apparently x to the 5 over k is the kth root of x to the 5. And you could keep doing a similar analysis for different numerators, and you would arrive at the following pattern, which finally sums up everything for fractional exponents. So x to the a over b, the fraction, the exponent a over b, that's the bth root of x to the a. There you go. That's the way that that mathematicians have defined fractional exponents. That makes the most sense because it agrees with our existing exponent rules that we developed for simpler exponents. Alright, so let's finish with some examples of using that rule. So, what are the following? 9 to the 1/2, 27 to the 1/3, 100 to the 1/2, and 64 to the 1 over, let's see, 1/8. Let's try, now let's just do 1/2 for right now. Let's do 1/2, 1/4, 1/8. Yeah, let's do that. Do 1/6. Yeah. Okay, so you might want to pause the video, try these now, and we'll end with these. So 3 again, 10, 8, 'Now this one is equal to 2. Let me show you how you might have found that. 64 is equal to 2 to the 6. So that the original problem is the same as 2 to the 6 to the 1/6 power. And we chose the definition of the fractional exponent so that all the old rules apply. So if you have stacks of exponents like on this, you can do 6 times 1/6, and that gives 2 to the 1 or 2. Alright? So keep that in mind, that all the old rules apply to fractional exponents. The power rule, the quotient rule, alright, stacks of exponents rule, whatever you want to call it.